All right, we're going to talk about segment relationships in circles, dealing with the segments of chords theorem first. So if two chords intersect in the interior of a circle, then the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. Okay, so let's say I have two chords, and we'll go ahead and label those chords. Let's label it A, B. It's one chord, and we'll go D, C. And I purposely tried to make it so those chords did not intersect in the middle. Let me kind of explain why this works and what the theorem actually says. So let's say I actually were to draw an angle here, and I'm going to kind of dash it out. Okay, from ACB, okay, and that angle right there, along with angle DCA. Okay, so if you kind of look at it like this, that angle and this angle, without losing sight of the chords we're dealing with, chord AB and chord DC. Okay, I'm using those angles to help describe what's going on here. So really what we know about those two angles, since they intercept the same arc DA, so DBA and DCA intersect arc DA, those two angles are congruent. Okay. I also know that I have vertical angles right here and right here. So if you were to label the point in the middle E, I would know that triangle DBE is similar to triangle ACE. And I know they're similar because of they have two angles congruent by angle. And the other thing I know about similar triangles is that in this case, corresponding sides, well, not in this case, in all cases, corresponding sides are proportional. So AE would be to DE. So this side right here to this side right here, as CE, so we'll stick with the same triangle, so CE is to BE. Then cross multiplying allows me to say BE times AE would equal DE times CE. And really what that says then is that this segment AE times this segment AE times BE, colors for this last part, this segment DE times this segment EC. Okay, so if I were to erase all of this mess, it's really quick, okay, and redraw in, oops, that was a C. And that's point E. I would know from this, from what we just talked about, DE times EC is congruent to AE times BE, or the product of the length of one chord, segment of chord times the other. So this times this is equal to that times that. Okay? All right. So let's apply this. Look at it in problems. Solve for x and use x to find AC and BD. So if I'm solving for x, what I know here is I know 4x plus 2 times 8 is equal to 9 times 4x. So this chunk times this chunk is equal to this chunk times this chunk. Okay, so multiplying it out, I get 36x over here. And on this side, I'm not going to stick with the color-coded, but 32x plus 16. Combine like terms, I get 16. Subtract 32x over equals 4x. So 1x equals 4. And if x equals 4, and I'm solving for AC, well, AC is this entire length. So 4 times 4 plus 2, that gives me 18 plus 8. So this side, AC, would equal 18 plus 8, or 26. And then BD would be 9 plus 4 times 4, or 16. So BD equals 25. All right. Let's try another one here. 3 plus 3x times 14 equals 12 times 4x plus 1. Okay, so we get 48x plus 12 and 42x, or 42, excuse me, plus 42x. Combine like terms, we'll move the 42x over to get 6x. Move the 12 over to get 30. So 1x is 5. If x is 5, AC equals 3 plus 3 times 5 plus 14. Right, these two put together. So that's going to give me 3 plus 15 plus 14, or a grand total of 32. Okay. And DB, or BD, equals 12 plus 4 times 5 plus 1. The 5 there. Or 12 plus 20 plus 1, or 33. All right. Take a look at some other definitions here. A tangent segment. Well, first, in order to have a tangent segment, you have to have a tangent. So let's go ahead and take a point out here, and we're going to draw a line that's tangent to our circle. We'll say it's tangent right there. I know that didn't quite hit it, but we're going to kind of say it did there. All right, we're going to call that point S. Well, let's actually go from point P out here. Okay, a tangent segment would go from P to S. It's just this segment right here. Okay. A secant segment would be a secant. So touches the circle in 2 spots. Let's go ahead and label that Q and R. And a secant segment is the segment that goes from the point on the outside, P, all the way through the circle to R. The external part of that segment would be the part that lies on the outside, so P to Q. And so technically the chord on the inside, I guess, would be your internal piece. All right, so using that, let's go ahead and talk about 2 other theorems here. If 2 secant segments share the same endpoint outside of a circle, so let's go ahead and put an endpoint here. We'll label that endpoint. Let's go E. We'll go A, B, and you know what? I'm going to just have it stop at the end there. C and D. right there. That's wrong mean. Now let's try that again. D. Okay. And what we know is then the product of the lengths of one segment and its external segment equals the product of the lengths of the other segment and its external. That's supposed to be an external segment there. Boy, I'm having a hard time writing that. Okay, so really what that says is EA, or excuse me, EB, the segment, times its external, EA, is equal to the segment, ED, times its external, EC. And there is a proof to go along with this, or a way to show it, kind of like I did on the previous one. It deals with similar triangles, and I'll just kind of sketch it out real quick, but I really don't want to go into it too much because it kind of confuses some students and messes things up just a bit. But if I were to create two triangles out of this, triangle EBC, and then triangle, let me erase this so you can see the other triangle, triangle EDA. Okay. Those two triangles I can prove similar. This angle would be, if I were to draw on the other one as well, this angle would be congruent to itself by the reflexive property, right? Okay. This angle right here would be congruent to this one because they both intercept the same arc. So by angle, these two triangles would be similar, which would mean that I could set up a proportion again. I could say EB is to ED as EC is to EA. And when I cross multiply, I get EA times EB and ED times EC. So same idea, right? That's kind of how we get that. And that'll be the same, similar idea if you're dealing with segments of secants and tangents theorem. So let's talk about that one real quick. Let's say I have a tangent. Okay, and we'll go ahead and label U, E, and A. And let's say I have a secant, and we'll label this point C and this point D. Okay, and so if a secant and tangent segment share an endpoint outside a circle, E in this case, then the product of the lengths of the secant segment and its external. Okay, so kind of the same idea in the previous one where you have ED times the external, EC, will be equal to, well, notice the tangent just has EA that you get to deal with. I mean, you could go EA times, well, there's nothing else to multiply by other than itself. So EA times EA. So it equals the square of the length of the tangent segment. So in other words, EA times EA, or EA squared. All right. So let's apply that there. Find the value of x. Well, so this says 4 external times the whole thing is 4 plus x equals 3, the external, times the whole thing, 3 plus 5. Okay, well, got to distribute. 4 times 4 is 16 plus 4x. And then 3, 16 plus 4x. Move the 16 over, you get 4x equals 8, so x equals 2. All right. Let's try another one here. Okay, so in this one we're going to have, a little tougher by the way. So we have a tangent, so we have 6 times itself, or 6 squared, is equal to the external x times the whole thing, x plus 5. So 6 squared is 36 and equals x squared plus 5x. Okay. Well, notice you have a quadratic, so if you remember back to algebra, you're going to have to factor. So move that 36 over by subtracting to get 0. The x squared plus 5x minus 36. I guess you could factor, use quadratic formula or graph or complete the square. But factoring is easier. Two things that multiply to make 5. Okay, for those of you who did the x method, multiply to make 5 and add the negative 36. Or excuse me, multiply to make, boy, I think I wouldn't have done it, negative 36 and add the 5. Okay, so in this case, positive 9 and negative 4. So we get x plus 9, x minus 4. And so the zero product property says if this times this equals 0, then one of these is 0. So you'd say x plus 9 equals 0 when x equals 9, or negative 9, excuse me. And then x minus 4 equals 0 when x equals 4. Okay? Well, notice we're dealing with a length right here. That can't be negative. So x in this case equals 4. All right, let's try another one here. One here. So we're going to have 4 times 4 plus x minus 8 equals 3 times 3 plus x minus 5. All right, so let's simplify the parentheses. We get 4 times, well, that's negative 4 plus x equals 3 times, well, that's negative 2 plus x, or x minus 2. Multiply it out, we get negative 16 plus 4x equals negative 6 plus 3x. Combine like terms, we'll move the 3x over by subtracting, so we get x and negative 6, and we'll move the 16 over by adding, so we get x equals 10. There we got it. All right, and notice they don't say find x here, they say find mn. So we actually have to plug that 10 in. So mn is equal to, well, that's this piece right here, x minus 8. So that's equal to 10 minus 8, or 2. All right, let's try one more here. Try to coordinate off here. In this case, we're going to have x plus 3 squared, because it's tangent, is equal to x minus 3 times x minus 3 plus 16. Okay, so it gets a little messy. X plus 3 squared, remember that just means x plus 3 times x plus 3. That means the same thing. If you remember FOIL, right? It's going to become x squared plus 6x plus 9 is equal to, and let's go ahead and simplify this over here to get x, and that's plus 13. Same thing, FOIL or distributive property. You get x squared plus 6x plus 9 equals x squared plus 10x minus 39. Move things around, combine like terms, so I'm going to move the x squared over, subtract it, so they're going to disappear. They're going to cancel out when we subtract. Move the 6x over, I end up with 4x minus 39 equals 9 by subtracting 6x on both sides. Add 39 over, get 4x equals 48. So 1x is 12. And if x is 12, Well, mn equals x plus 3, or 12 plus 3, which is 15. All right. One last piece, find the radius, circle A. Okay, so using the same ideas, right? We got a tangent, so we still have 18 squared is equal to, well, we have the external, 6, times the whole thing. Well, that's 1, 2r plus 6. All right? So here we're going to have 12r plus 36 equals 324. Subtract 36, we're going to have, oops, what happened? Well, my pin's not working. Hold on a second. All right, good. Subtract 36, we get 288 equals 12r. And then we'll go ahead and divide 288 by 12, and we end up with, come on now, 24. There we go. The radius is 24. All right, that's all I got for you. Good lucky.